Hello, this is Mr. Craig, and I want to talk about more kinetics here. This is topic 8, part B, which is day 102 if you're in my class. Yesterday, or the last time that we met, we discussed the reactant orders for an individual reactant when we had more than one reactant. Again, to refresh your memory on that, the only type of order that we care about is a zero-order reactant, a first-order reactant, or a second-order reactant. And again, what a zero-order reactant does for us is that if we change the concentration for a zero-order reactant, the rate does not change regardless of what the concentration is. If we double the concentration for a first-order reactant, we double the rate. In other words, it goes twice as fast. For a second-order reactant, if we double the rate, it's exponential, which means it'll go 4 times faster. And then it'll work in the opposite direction too. So if we have half the amount, then that'll also be affected accordingly. Well, today what I want to talk about is the overall order for a reaction. So in our notes here it says overall order. If I have a reaction where, say, I have 3 reactants, and maybe the first one is a first-order reactant, the second one is a second-order reactant, and the third one is also a second-order reactant, we would add up the orders to get an overall reaction order. Now, those do not have to be 0, 1, or 2. And in that case that I just said, with the first order, second order, and another second order, the overall order for the reaction would be 5. So for an individual reactant, yes, you can only have 3 choices, or 3 choices that we care about for the AP exam. So when you are asked to determine the overall order for the reaction, add up all the orders. All right, we talked about first-order reactions or reactants the last time we spoke, and on the AP exam, there's an equation that looks like this right here. And that's on your equation sheet, and you'll find that on the kinetics section on your equation sheet. I believe it's on the front side lower left-hand corner. It's either the second or the third from the bottom corner. And what this is saying is that the natural log of the concentration of A at some point in time minus the natural log of the initial concentration, that's what that little 0 right there represents, and T represents some point along the reaction, is equal to the negative value of the constant K times T, which is the temperature. We could also write the equation to look like this, where the natural log of the concentration at some point in time over the initial, and that's saying the same thing mathematically speaking. If I take the natural log of A minus the natural log of A initial, then I can divide those out. So either way you want to work those, work that equation out, that's fine. There's nothing wrong with that. However, we have to realize what these variables represent. So again, the T is some point in the reaction, and typically what that means is how much still remains, and again, the 0 is your initial amount. And we'll do some calculations here shortly to show how this works. One thing that I want to talk about is looking at the negative K here. The reason why that value has a negative value there, if we scroll down here, you'll see 2 graphs. The graph right here, the one on the left, actually shows a graph in representation of the natural log, the concentration of A versus time. And again, there's that deceleration or that curving slowdown, so to speak, of the reaction. In other words, it's always going to be quickest at the beginning, and then it slows down considerably near the end of the reaction because we don't have as many reactants. However, if I want to check and see if this type of reactant is a first-order reactant, I can take the natural log of A versus time, and it will yield a negative slope. There's my straight line. If I get a straight line with a negative slope here, then that means I have a first-order reactant. So when I go back to my equation and I see negative K, my negative K is indicative of this negative slope. So on the AP exam, in the multiple choice section, you may be asked to determine what the order of a reaction is simply by looking at the graph itself. Now, it wouldn't be fair for you to be asked a question where it says the concentration of A versus time and you see a deceleration, because that could represent both first or second order reactants. Now, it would not represent a zero-order reactant. Remember that a zero-order reactant does not change the rate based on the concentration. So if I had, say, just the concentration of A versus time, then that would generate a negative slope. But that natural log there tells me that's a first-order reactant. Half-lives. Typically when we talk about half-lives, most half-lives that we deal with, especially with like nuclear reactions or a lot of other reactions, typically are first-order reactants. Half-life, again, tells me it's an amount of time that it takes for half of the amount that we started with to decompose or to disappear or to change into products. So whatever that amount of time is, that time will remain the same for each half-life. So in the graph here, I have, looks like about 100 days is the half-life period. In other words, I started off with, looks like 0.1, and then after 100 days, I had 0.05. After another 100 days, I would expect there to be 1/2 of that 0.5, which would, be, in this case, be around 0.025. And then after each 100-day period, I would expect there to be half of the half. So we can do some calculations knowing what the half-life is. We can determine how many half-lives this has gone through. We can determine how long it takes to reach the half-life. We can actually calculate a couple other things based on that. I don't want to give that away just yet. So when we do a half-life calculation, there's a shortcut here. I mean, yeah, you can take the 0.693. What that is if you look at your equation here, actually it's a little simplified, and I don't really like to show this equation in class, but if I take the natural log of half of the concentration over 1, then that will give me, natural log of that will give me a negative 6.93. Now that negative value up here is because I have a value that's less than 1 for the natural log. However, the negative k down here is where I bring that negative k down below the 0.5 over 1, and then that'll give me my half-life time. So whenever I work these types of problems out in class, you will always see me put 0.5 for that concentration. I will not use this 0.693. I don't want you to have something else to memorize. I would rather you be able to use this equation. Some of you may be able to remember that number, and that's fine. Just as long as you're showing your work and showing all your steps, the graders will be happy with you. But if you just go ahead and type that information in and write the answer down, you probably won't get any credit for it. So again, always show your process here. Continuing on here, I'm just showing the process of how I work out a half-life problem, and I'm going to do one like that here momentarily. So I think that concludes the first sheet here, and this one was mainly dedicated to first-order reactants, even though I have second-order on there. Examples part 2 will discuss second-order reactants. So let's take a look at that video.